Paul. Paul had mentioned that 2 years ago he knew nothing about this stuff, and I would say a year ago I knew nothing about this stuff. I'm still learning, and so as we go through this and I start to talk about things, by no stretch am I an expert in, I'm not a data scientist, but Paul alluded to this fact that, first off, data is a huge part of AI. And that's why it's increasingly becoming important for those of you that are data professionals, those of you that deal with AI. You'll be involved in some way at some point with this stuff, so it's kind of important to kind of get a good understanding on some of the terminology and stuff. So that's kind of what this slide is. I work with data. I'm not a data scientist. I'm not an AI person, you might say, but why is it important? Well, again, this is where the world is going. Good to know this stuff. The big thing is good data is fundamental to good insights. If you've worked on projects around data warehouses and data marts for analytics and things like that, data is important. Clean data, data that you know where it came from, that you can trust. That's even more critical with AI. Because a lot of times, obviously deriving insights from data in the past, what comes out is very important. But now, these could be having even more direct impact on people, on your clients. And in fact, there's regulatory reasons where, if an AI decision is being made in some industry, it's got to be explainable. If you, in some countries, tell someone, you know what, you've applied for this loan, but, computer says no. Well, why did it say no? A lot of cases, you have to be able to explain this stuff. So data provenance, data governance, really, really critical. So, I mentioned data scientists earlier. Who are these people? Do we have any data scientists in the room? No, otherwise you'd be out in your yacht spending all the money you get, because they're in high demand. People want them. Reason being, they've got this kind of great set of skills around computer science, statistics, math. The really good ones have a really good understanding of the business that they're working in as well. And so you'll often hear them referred to as unicorns for this kind of convergence of skill levels and experience. As I said, they oftentimes rolling in money. Me, I'm not a data scientist, but I play one at Db2 conferences. But that's not actually true either. Some of the stuff I'm going to be talking about, it's the basics. And so that's what I'm going to be helping you along with here. But get into the deep dive, some of the stuff, like, I don't know, stochastic gradient descent. I can't even spell it, let alone, or say it, let alone know what it is. So, don't ask me really tough questions about what algorithms are doing. But I suspect we probably won't need to get into that detail anyways. But let's start off with kind of, whoops, what happened here? All right, we're done. I've lost this. Marketing type stuff, just, why is AI important? The fact that you're here, I think you probably already have an idea, and Paul talked about it as well. So now let's get into some of the kind of the terminology, the lingo, the stuff that you need to do to know to get started. And this was kind of what Paul was referring to when he said I had this kind of Russian doll, subset of definitions around this. So artificial intelligence, and he said when he talked, artificial intelligence, machine learning, deep learning, he was considering all of those the same thing for the purposes of his discussion. But just looking kind of at artificial intelligence being this wider thing, really it's about systems that are mimicking human intelligence and actions in some way. Oftentimes you'll see it kind of broken up as general AI, so kind of having the ability to do everything or be able to think like a human and do multiple problems, types of problems and stuff like that. Or narrow AI, where you're very focused on a particular domain of a problem and a problem that you're trying to solve. Now, a subset of that is this thing called machine learning, which is essentially where machines or systems are learning from the data that's being presented to it. So Paul showed the case of all the letters of the A's, right, and then the multiple different letters. So those would be kind of these machine learning problems. Or it could be a matter of you're feeding in customer data, or I'm going to probably use the example of defaulting on a loan or a mortgage application, where you have this history of data associated with clients, and did these people default on their home mortgages or on loans? Would they be the right kind of people we'd want to give loans to in the future? So again, you're learning from that data to be able to make predictions about the future. So that's machine learning. And then the subset of that is deep learning, where really we're talking here about image, video, audio processing, natural language processing. So things that are, again, we're learning from data coming in, but we're more focused on things where they're quite difficult. There's some level usually of context to it, and oftentimes what's being used for these problems are neural networks. So that's the kind of the algorithm or the process that's being used, and that's where this deep learning name comes in, because you're typically talking about neural networks that are deep, and I'll talk about this a little later, and so that's where this name comes from. So really, all of this is about identifying patterns in data and making predictions. And predictions might mean, yes, this person's a good fit, or it might be, the pictures of this particular piece of equipment on the assembly line look like there might be damage there. So yeah, damaged, yes, damaged, no, or more likely some percentage of, does this look like there's a problem here or not? And then there's also the term data science. And often you're going to hear me as I go through this kind of talk about this, in the same way as AI. Really, though, data science is more of this process around it, in terms of having hypotheses that you want to find data for to help support or to help refute, then go through the processes of using AI techniques to come up with results, then sharing those results with the business, evaluating those results and things like that. So this is more of the kind of this wider process of data science. And lots of different use cases. You can just Google artificial intelligence and a particular industry, and you're going to see thousands, if not tens or hundreds of thousands of hits around what different industries are doing with respect to AI. So what does a common data science problem kind of look like? Typically, you're going to identify some sort of problem or prediction that you're wanting to make. You're going to need to figure out what data you need. Typically, this is going to be an iterative process. In fact, a lot of data science is iteration with respect to getting the data you want, with respect to doing the training of models. And then over time, the accuracy, or as Paul said, the performance of models, they may get reduced over time. So you need to revisit that and maybe do retraining. So it's all very much an iterative process. But again, data, very, very important and a big part of this. So just like your ETL that you do for your data marts and your data warehouses, getting the data in the format you need, that kind of stuff's important and is so for AI as well. And then the big part that's often talked about around machine learning is training models and evaluating models. So I'll talk about that in a bit. So if you look at kind of how AI is used within an enterprise, typically, you've got all this data. Again, there's problems that you want to solve. There's insights you want to glean from it. You got to shape and clean that data. You got to build models, train models. Then once you've got a model that you've trained, that you're happy with, that has the performance, the accuracy levels that you need, then you're going to look to put these things into production in some way. Typically what happens is, coming out of this model building process, you end up with a library or code. It could be Python code or something else that you're then going to host somewhere, and oftentimes it will have an API to it, a REST API usually, from which then an application then can call in and make these predictions. So again, if it's like a bank loan example, maybe you've got code that says, you're feeding in information about, what's the person's net worth, or what's their income, how much do they have in the bank, what are they employed, how long have they been working. Those kind of things are going to be fed into this algorithm. So the application developer would perhaps have this kind of information being taken in from a customer on the website and then calls this REST API to do the prediction. And often, as I said, it's an iterative process, so you're going to go through this multiple times. So just looking at this in another way, there's a lot of folks that are typically involved in this. So you've got the kind of data engineer, the data people, that may be where you're fitting into it. This data is extracted from your systems of record, wherever it is. It could be structured data, it could be unstructured data, it could be a mix of these things. The data scientist is then going to do some of their own data preparation. They're going to go through a process typically called feature engineering. What feature engineering is, and you hear this term quite a bit, features are essentially your columns of data that are coming in, so attributes of your data. But sometimes that data isn't in a format that really works well with these mathematical algorithms. And so it needs to go through this process of saying, perhaps converting that data into a format that's better suited. Or maybe it's something like, if you're doing an analysis of past transactional, like retail store data, and want to be able to predict what are my sales potentially going to be like on this future date, you are very likely going to have a date associated with your past transactions. The date on its own might not mean anything, but whether that date corresponds to a weekend or a holiday or something like that, that could be very important. So the act of taking your date column and maybe making a column that says, is this a weekend? Is this, or pull out the day of the week, or pull out the quarter, or something like that, to a more mathematical type of thing that has significance to it. That's what feature engineering is. Also, they'll do weird things, data scientists, where they'll take multiple columns and put them together in some way to come up again with things that the machine learning algorithms might be able to work with better. So that's what the data scientist is doing. And then they're picking algorithms that they think might help. If you're doing a classification problem, there are some well-known algorithms that typically get used. So they'd be using that, and then they'd be going through the training process, coming up with a model. They're going to work with the business person who knows things. Again, if it's a loan application or something like that, you're going to work with someone who says, okay, here's the predictions being made on this data. Does it look right? Does it look like it's coming out with the right stuff that you'd expect? If not, maybe we're not using the right data. Maybe we have to do things differently. So there is that, working closely with each other on it. DevOps, putting it into production. The application developer, like I said, changing their apps or writing new apps to call these APIs to be able to take advantage of these models. And then monitoring. This isn't a thing where model's done, the data scientist throws it over the wall to the application developer, DevOps people, and says, I'm wiping my hands of it. It's not the case. Over time, the accuracy of the model might get worse. And so you might have to go through this process. So you always want to be kind of monitoring things and managing them and looking at the health of things. So again, very iterative process here. So I've said model quite a few times. And in fact, if you go to look up what's the definition of a model, it's really hard to find, because you'll find papers on stats, because that's kind of where it comes from, and math papers and machine learning, deep learning stuff. So when I think of a model, I basically look at it as a mathematical representation of some real-world process. And that's been based and built by finding patterns in the data. Once you have this model that's used to make predictions against new data, it's typically built from some mathematical formula or algorithm, or a combination or ensemble of these things, where they themselves have some number of parameters whose values are learned from the data. So you can think of kind of the most basic example, where maybe you've got a data pattern that follows some straight line. There's a single X input and a single Y output. I can't remember what it was, but there's this case where some, I don't know if it's cricket or grasshopper, where depending on the temperature, it makes so many chirps. And it's a straight linear line based on temperature. So this is the old, y equals mx plus b, slope of the line plus the intercept kind of stuff. It's a very, very basic model there. Now, let's say you've got a whole bunch of data points, and the training process is essentially going, okay, find that line that fits things best. So it's going to be adjusting like the M's and the B's in this case. And so it's going to do that by running through the data points coming in and comparing it to the outputs of known values and coming up with this value. So that's this training process that you've got. Like I said, once you've built a model or you've trained the model, you may actually, or the data scientist may find that putting some of them together or multiple ones together comes up with a higher level of accuracy. All right, so data types. This will be nothing new to you, right, as database people, but you could be dealing with structured data, tabular data, unstructured data like audio, images, videos, things like that, or semi-structured data. All of these things can come into play depending on the type of problem that you're working with. Training types, kind of the main training types you'll hear about are supervised learning, unsupervised learning, reinforcement learning. So these are things Paul got into a little bit in his presentation. Supervised learning is where you're basically providing labeled data already. So you're saying, I've got some data, and given that data, here's what I expect the output to be. And again, it's typically based on just past things that have occurred. This could be simple tabular data. It could be a matter if you're dealing with images saying, yes, this is a dairy milk bar. Oftentimes when you're dealing with images, you're not just providing one picture, you're actually providing a whole bunch, because picture could be taken from far away, color could be different depending on lighting conditions, positioning. You end up providing a lot. In the case of the tabular data here, again, this doesn't mean anything, but a couple inputs and an output. It's a classification problem. It's either true or false it's trying to predict here. So here's kind of a simple example of that, which is, here's the age of our client, their income, did they pay their last month on their credit card, and what's the prediction of whether they're going to pay it this month, or maybe it's a loan thing. What's the chance that they're going to default on their loan? So having this historic data, is there a pattern in there that we could then use to be able to actually make predictions on new data that's coming in? So again, that's kind of the foundation of supervised learning. Two main types that you'll run into are regression. So how much will a customer spend, for instance? What are what do I expect sales to be this coming summer or this coming weekend? Or again, a cricket, given the temperature, what can I expect the chirp rate to be on that? So that's regression. Another type of supervised learning problem is classification. Essentially, like, will a customer make a purchase? Yes or no? Is something going to be true or false? And so that's when you'll often see too. So unsupervised learning, on the other hand, is where there's no label, there's no specific prediction that you're trying to make. Really, this is about trying to understand patterns, different types of algorithms that you'll see here as well. A common one that you'll see is something called k-means, which is essentially find clusters of data in the data points. This could be useful for things like customer segmentation and trying to find customers with like characteristics. Maybe these are your customers that have similar income and savings and stuff like that, which means that you could potentially be doing targeted marketing to this group of people that might be a little different than this other group of people. Data splitting. So this is an interesting one. Again, if you go and you start looking at this stuff online, it's not cut and dry. You'll find people do things a little differently, but data is, as I said, very, very important to kind of training your models. So what often happens is you have to have some portion of the model for training, some portion for what's referred to as validation, and then some used for test. So remember I talked about this model building and training process being very iterative. So let's just think of that case of that, y equals mx plus b, a straight line. So the training process itself is going to, let's say we've said, okay, we believe we're going to use this simple algorithm. We're going to feed it all these x's and known y's for those. And again, it's going to find the line, the slope for that. It's this training data that's used to do this. Once you've got a model, and I'm going to skip to the end here for the test. Once you've got that model, you want to make sure that you didn't fit it specific to that. And I'm going to get into overfitting shortly, but you want to make sure that what you've come up with is a pretty generalized model that's going to work well even for data it hasn't seen yet. And that's where this test comes in. So it's data that is not seen at all as part of the model building, model training process. And so it's a good way at the end to say, okay, how successful was I? How accurate was I in predicting data that it hasn't seen before? Now there's another kind of set of iterations that come in here. When you're doing this model building, oftentimes what happens is there's the parameters that you may be adjusting during that training process, but there's also some kind of higher level structural parameters associated with the algorithm. For instance, the learning rate. How much, as we're going through the training process, are we going to, let's say, go try this line, but maybe I'm going to try this line, or maybe it's going to try it like that, or maybe it's going to try it in little increments. Those are referred to as hyperparameters. If it's something like a neural network that we're talking about, it might be how many levels are there in the neural network. Or if it's a decision tree, sex, male, female, you go down the tree. Okay, income greater than this or less than this. That's a decision tree. How many levels you have in the decision tree, or how many nodes there might be. These things, again, are referred to as hyperparameters. And so the data scientists adjust these things because maybe the parameters used for one type of problem aren't good for another. So it's this other level of iteration that happens. Not only are you trying to find that line as part of training, but maybe you're starting to adjust, again, the learning rate or how many times you go through this training process and change these hyperparameters. That's where this validation data comes in. So again, it's data that isn't directly seen during training, but as part of it, as part of this iterative process, it's using this to say, okay, am I on the right track? Am I still doing okay here? Am I kind of potentially overfitting my data, and so on? So if you're working with people, data scientists, they may be looking to you to say, okay, I need randomized 80% of my data for training and maybe 10 for validate, 10 for test, and so on. Complexity. So I've been talking very simple examples, and X input gives you a Y output. So this kind of like 2D graph. You add in some, another input variable or another 2 input variables, and all of a sudden you're increasing the dimensions 4D. It gets harder and harder for you to actually visualize this stuff and keep it in your head. It's very easy to look at a straight line and understand what that trend is. It gets more and more difficult as you start to increase dimensions. And in reality, what you're typically dealing with is tens or hundreds of dimensions. Being database folks, you deal with data with tables, transactional tables that potentially have tens or hundreds of columns. And so this is where it gets really, really tough to again, visualize. So what the system's actually doing and what all these different deep learning and machine learning frameworks and algorithms are dealing with are numbers. So Paul mentioned it, when he said whether they were A's or whatever it was, or Super Mario Brothers. At the end of the day, it's numbers that these things are dealing with. So just to give you an idea of some of the terminology here, and for those of you that have taken math, and it's been far too long since I've taken this stuff, but I do remember some of these terms. Scalar, kind of single value. Vector is an array of scalars. You work up to matrices, where they're kind of this two-dimensional array of scalars, or kind of an array of arrays. And then you get to kind of this next level of what are referred to as tensors. And so if you've heard of like TensorFlow, which is a common deep learning, machine learning framework, That's kind of where the name comes from. And so here you actually have matrices of matrices. And it doesn't have to be like this. Each one of these could be a matrix and so on. And so this is the type of data that these things work with. And so if you've heard or seen that GPUs, graphical processing units, are often used with machine learning problems, it's because this is what those things deal with. It deals with these things very, very efficiently and effectively. Hence, they're often used for doing the training associated with machine learning and deep learning workloads. So let's dive a little bit deeper into machine learning. So I mentioned kind of the regression type problems already. You know, you've got kind of this linear regression type of case where, again, this is kind of a straight line here. Here's like that y equals mx plus b type of example I was talking about. Here's another case where, oh, this is still a linear regression problem. It's just this isn't fitting it. You know, a straight line isn't fitting it. And so, you know, you'll often see algorithms of the form or the named like logistic regression and polynomial regression, which are still linear. They just don't happen to be straight lines. But again, thinking back to math days, it's really all about just trying to fit to these lines. Again, we're looking at 2 dimensions here, but really what the system is trying to do is, regardless of the number of dimensions, it's trying to find a line that fits them. Now, I mentioned overfitting and underfitting here. And overfitting is the case where it's kind of too smart for its own good, the model, where it's, okay, I've come up with a 100% accurate model here, or a near 100% accurate model. And really all it's done is it's learned specifically how to handle those data points it was given. The problem with that kind of thing is if you're now to feed new data to it, there's a very good chance that it's going to predict or behave poorly on that data. So you're going to have to look to potentially feed it more data as part of training, or kind of just look at your data and make sure you're giving it kind of what it needs. Underfitting is just where you haven't even really come up with something that's good. And again, typically you need to give it more data. A lot of times it comes down to more data. More data you have generally means more accuracy, better performance. I mentioned clustering and k-means clustering before. This is really just about where the system is trying to find, again, trying to find groups or clusters of data that are similar. Oftentimes by trying to find kind of the central point and calculating distances from them. And in the case of these k-means clustering, an example of a hyperparameter, remember I talked about hyperparameters being more around the structure of the algorithm. That might mean, okay, maybe here we told it look for 4, but maybe 5 clusters or 6 or 10 or something might be more appropriate for what you're doing here. So the data scientist would say, okay, let me try looking for just 3 clusters, or let me expand it out to 6 or 10. So again, this iterative process that they'd be going through here. So deep learning, as I said before, comes from the fact that we're dealing and using neural networks as part of, for the algorithms that we're using. Neural networks, essentially they're designed to work kind of in a similar way as the human brain. You have inputs, you have some kind of intermediate layers, hidden layers, and then some output type of layer. Very simple here, where you've got a single hidden layer. You can have deep learning neural networks that go out to many, many, many different layers. Each layer is typically associated with some level of processing. In image processing, it might be a matter of, the first layer is identifying edges. And then the next layer is identifying where the edges come into, where they meet. And you start going on, and they're identifying more and more features. I couldn't talk. Someone could talk for hours about how that actually takes place. That's a very simplistic view of how these things work. But the fact that you have, and you can have, multiple hidden layers here, that's where this term deep learning comes in. And so what happens is, as part of the training process, and it's being fed data, and again, this could be pixels associated with an image, and we're trying to say, maybe you got an image classification problem. Is this a dog? Or is this a cat? Or it might be it might be an object detection where it's find me the dogs and the cats inside the picture. So again, it could be these pixels coming in and identifying different characteristics of the picture and ultimately coming out saying, yes, this is a dog. Yes, this is a cat. And so the training process, what happens is you've got, whoops, I'm going to skip back in a second, but these weights and biases. Essentially, it's just numbers that say, okay, the higher the weight, the stronger this connection is. When you're a kid, when you're learning stuff, you're very young, your parents say, that's a dog. That's a dog. That's a cat. But, the 1-year-old or 2-year-old points at the water bottle and says, dog, cat. They're like, no. So it's this reinforcement of when you make the right prediction, the weights and the paths through here get stronger, makes a poor prediction, the weights get reduced. So this is this process of training when you're dealing with these neural networks. Whoops. And so Paul mentioned this as well, and I certainly don't expect you to remember what these things are, but I've only included them here because they are the kind of common ones you'll see when dealing with neural networks. You've got the convolutional neural network, and Paul said, if you see CNN, convolutional neural network, think image processing, because that's what it does. Really what it's doing is it's going multiple times over the image. Again, really what you're dealing with is pixel data. Again, it could be something like just the RGB numbers for a particular pixel that are being fed into this. Recurrent neural networks, here what happens is there's some form of kind of data being passed back. Outputted one might be being passed back into the same layer, giving context to it. So you'll see this a lot with natural language processing because there's context. If you've got some word, looking at a word might mean nothing. But when you put it in the context of other words, it could dictate its meaning, or it might change its meaning depending on the other words around it. So these often, as I said, come into play around natural language processing. So this is just talking a little bit more about the hyperparameters. Again, these being those kind of higher level parameters associated with more of the overall design or architecture of the algorithms themselves. Again, in the case of a neural network, it might be how deep, how many layers do I have. It could also mean how many iterations, or what are referred to as epochs, of going through this process before I just stop and say, here's the trained model I've come up with. If you're going to go through the model 1,000 times, versus going through it 10,000 times, it's a good chance that having gone through it 10,000 times and adjusting things along the way, you're going to come up with a more accurate model. How much more? Could be 0.5%, could be 0.1%, could be 10%. But even then, what does that mean, right? What is the difference of 1% on a business outcome? It could mean a lot. It could mean a little, could mean a lot. If it's something around health and it's identifying tumors and cancerous tumors, 1% is a big deal. 0.1%, I would argue, is a big deal, right? So that's why this stuff is iterative. And again, it can take days, weeks, months to do this training. So that's why it's really important, and I won't get into infrastructure, but servers, GPUs, all that kind of stuff comes into play. The faster you can do this training, the more accurate you can get it, and of course, the more work you can do and the more problems that you can solve as part of it. I'm going to skip that. So ultimately what happens is when you build a model, as I said before, you get this model, this code out of it. In the case of neural networks, it's typically going to be kind of the algorithm associated with that neural network. What are the functions that the different kind of nodes and output layers are doing, along with the weights and biases associated with it. And so ultimately what happens is you take that, and again, it's hosted with an API call typically, and your application developer can end up using it. I mentioned TensorFlow. This is a fairly fluid thing. Has any of you here used any of these things before? All right, a few of you. Yeah, I know Callisto's used it before. You know, if showing this 2 years ago might have shown a different set. Well, I mean, TensorFlow, Cafe, and stuff has been big, but it's a pretty fluid area, a pretty fluid in terms of you'll see other companies like H2O, which I'll briefly mention a little bit later here. You'll see a lot of different things, and some have become popular, some haven't. They're open source, typically all of this stuff. And like many open source things, popularity of some goes up, popularity of some goes down. But these are kind of some of the main ones at this point in time. So I mentioned the fact that typically when it comes to deploying a model, it's going to be hosted somewhere. An API call is going to be available for it. You're going to pass in some data, and a prediction is going to come out of it. And so this process is typically referred to as scoring or inferencing. It's inferencing or inferring a result. Thank you. And so you'll see these things kind of used interchangeably here. And oftentimes what happens, and on this one, is there's kind of a couple things that are talked about when you're talking about accuracy and how well something is doing. So the accuracy, as I've been using it, is talking about kind of the overall model that you've built. How accurate is it? And that comes from looking at the test data that was fed into it. So that's one number that you'll hear about. The other one is around confidence. And this has to do with individual predictions that are made. So if you're doing something like an image recognition or an image detection or classification problem, or perhaps you're doing like, was this person, you know, are they a good candidate for a loan? It isn't usually just a yes or no answer. There's a confidence level that comes along with it. And you can kind of determine what's the threshold for what I'm willing to say yes. You know, again, maybe if you're looking at MRI images and trying to determine cancer or not, you have to determine, you know, do I look at lower thresholds because maybe I want to get ahead of things? And so while the model doesn't think it is, there's still a chance it might be. So you might want to look at that. So your application is typically going to look at the confidence level and say, you know, is this something I want to look at further, perhaps? So in this particular case, it came back and said, okay, I think this is this cream egg, you know, 95% confident it is. Or if it's an image detection thing where there might actually be multiple things you're trying to find in an image, you might say, okay, I found all of these things, and each one may have its own individual confidence level. So speaking of images, just to kind of get across some of the terminology, and I've used some of these terms already, a few different kind of problems that people try to solve around this. So there's classification, looking at the whole image. Is this a cat? Is this a dog? Is this a zebra? Versus object detection, actually find me objects in there. So if I give it this picture, you know, what's in there? You know, well, there is a dog. There are two cats. There is a rubber duck or something there, right? So those are different kinds of things where it's just like an expectation of one thing in the picture versus multiple things in there. And kind of the next level up from that is referred to as segmentation, which is actually saying, okay, find me the boundaries of these particular animals here. And, you know, essentially any one pixel can only identify with any one image here. So again, that's referred to as instance segmentation. So looking at Db2, and I don't want to spend a lot of time here. Really, the point is just showing, and you've probably heard this already, is there's a big focus on Db2 being the database for AI, both from the perspective of being able to use it as your kind of source for data that you are going to build your AI models from, as well as being able to actually have AI infused into the system with respect to like our machine learning optimizer, The experts there, so go see. I assume you're talking about this stuff at some point next, Callisto? Yeah, so go see his presentation to learn more about that. But you know, there's a lot of opportunity here to be able to use AI and machine learning to you know, make improvements just by looking again at DB2 is all about data. Even internally, the metadata, the stats we collect, looking at data as it's passing through the system, being able to then make intelligent decisions based on that data is a huge opportunity here. Now, if you're looking to, whoops, I assume you go through this, so I don't want to spend too much time on this here, but let's get into some next steps. So if you're looking to actually do some work yourself with this, there are code patterns available, and you can do stuff. There's a lot of stuff around Python that's available to you out there, and I've given you some links. So a good kind of getting started guide for AI and DB2, along with some different tutorials that are available to you. If you are looking to do stuff with Python, a great way to do that is through Jupyter Notebooks. Anyone here use Jupyter Notebooks before? Okay, a few of you. So this is just a great kind of graphical browser-based way of writing code and executing code in a very interactive way. And so you can do your Python programming in there, for example, along with some other languages as well. So there's a link down here. But you can just see, just for an example, like fetching a row of data or connecting to the database. You can run this Python code and write your Python apps to be able to interact with DB2. Now, for those that are just looking to improve your data science and AI skills overall, I've put some links to some of the more, you know, kind of common ones that you'd see out there. Big one that you'll often read about or see is Kaggle. Thank you. How many of you have heard of Kaggle before? All right, it's the same hands typically that I've been showing here, but really this is the kind of world's largest data science community, best known for AI competition. So what they'll do is companies will come to them, give them anonymized business data and say, we're trying to figure out this problem. Again, it could be Walmart trying to figure out or predict future sales. NFL did something recently, National Football League in the US, around predicting the accuracy of its kickers. So they'll put up some money, $25,000, $10,000, something like that, and data scientists can come and build their models and put it up against everyone else and try to win money. So if you're interested in making money, want to get in, that's a great place to do it. But in addition to that, they also have a lot of sample code and Jupyter Notebooks and what they refer to as kernels or environments for running stuff that makes it really, really easy, as well as public data sets. So if you're looking for data that, you know, interesting data you want to play with, they've got a lot of data on there. And then from kind of a software perspective, you know, it's more kind of salesy type stuff, but you know, we've got some capabilities around collaborative machine learning, development and deployment and monitoring through Watson Studio and Watson Machine Learning. Cloud Pak for Data, you'll probably hear about quite a bit this week here. This is kind of a platform that includes these capabilities, among others, as well as databases like DB2 and Postgres and MongoDB. So as a Kubernetes container-based platform for easily deploying software. Paul was showing some examples with Power AI Vision, which is essentially automatic deep learning capabilities where you can just drag and drop and say, okay, you know, he showed like the hard hat, the safety vest, and that kind of stuff. You can go in with your own pictures and just say, this is what a safety vest looks like. This is what a hard hat looks like. And actually then have the system build a model where you can drag and drop new images and it will do the identification and classification for you. I was planning to do a demo, and I apologize for not being able to do it now just because of the time that we lost earlier. But a partnership that we have is with a company called H2O, and they have this program or this application called Driverless AI. And it's actually pretty amazing. If you've got a chance to go out and download it and try it out, it's automated machine learning. So essentially what you do is you feed it data, and you can get data from DB2, so through a JDBC connection, and I've got some slides in here that show how to do that. and you can build a data set and run an experiment, what they call an experiment. All you do is you say, here's my data set, here's the column I'm trying to predict, and go. And it all automatically determines, is this a regression problem, a classification problem? It automatically goes out and does feature engineering, goes through and tries different algorithms, tries different models, and then boom, you're given a model at the end, which you can then download as Java code or as Python code. Very, very simple to do. So that's actually a trend that you'll start to see more. In fact, we're even doing that as part of our Watson Studio and Watson Machine Learning offerings, is this automated machine learning. So, I talked a lot about feature engineering and training and stuff like that. Data scientists are going to continue to be deep into that, but for the more novice or junior data scientists or organizations that don't even have a full-fledged data science team, these automated like deep learning and machine learning capabilities are going to become more and more important. A big part of those as well that you're going to see, and Paul alluded to earlier, is around ethics and actually deploying things. So being able to determine, is there bias in the models that I'm building? If I'm feeding it data that, let's just say there's cultural bias. If you had an algorithm that is predicting how much time should someone get for a crime, if you go and use past data, it may be that the justice system has been particularly hard on certain socioeconomic groups. You don't want the model that you're building to actually propagate and continue with that bias. So being able to determine where that bias is, being able to audit the decisions. Why is it making this? Do we need to actually give it more data? If it's something around a sex, male and female, and making a determination, if you give it 90% of the data is related to men and only 10% is related to women, that might not come up with an accurate representation or accurate predictions as well. So all of this is really, really important. And so the explainability of it, the auditability, again, all these ethical stuff around it, that's a major, major thing going forward. And again, you'll see stuff coming. In fact, we do have something called Watson OpenScale. And driverless AI has this built in as well. So this is more reference material. I know I'm ending right now. If you do try out driverless AI, there's a link to a 21-day free trial there for the software. I give you some information about setting it up. In addition to building models, you can actually, they provide a batch script that lets you go off and pull data from Db2 and do scoring on it and put the data back into Db2. So I've got a full deck that I've built on that, and I'm trying to figure out what I'm going to do with it at some point. But if you have interest in trying this stuff out, reach out to me, and I'll send you a copy of that deck with all the instructions in there that you can try out. So this is just showing, again, reference of how to actually get at Db2 data, and likewise around Watson Studio and Watson Machine Learning, which are a part of Cloud Pak for Data. You can go after Db2 as well. So with that, again, apologies. I wanted to do the demo, didn't have time, but if there's any questions, it's been pretty quiet so far, but I'll be sticking around either in here or outside for a little while. So please feel free to come up and ask. Appreciate your patience in the technical difficulties earlier, and just generally really appreciate you coming out, and thanks for that, and hope you have a good conference.